Right, hello everyone. So we are waiting for our speaker.
Hello, everyone. So I'm in. So ready for the presentation.
Hello, Dr. Suramate. How are you?
Yeah, I'm fine. Thank you, Professor Asrami. Nice to see you.
Yeah, nice meeting you virtually here.
Yeah, sure.
Well, actually, Jack is just beside me, next to me now.
I see. Okay.
But anyway, can we wait for a couple of maybe 5 minutes and then before we start?
Sure. I have time, so no problem.
Yeah, we are getting more and more to come. I don't know how many have registered, Dr. Noramina. How many have registered? Dr. Noramina?
Yeah, 52.
52. Okay, so I think more will come. Okay, Suramate, more will come.
I see. Okay, no problem.
Suramate, probably you would like to share your first speech, then we can see whether it's okay or not. The slide, yeah, your slide.
Slide. Okay. Yeah. So I will give it a try now.
Yeah.
So one moment, please. Not there yet. Wait.
สวัสดีครับดรสุรเมธ
สวัสดีครับ อาจารย์เพลินเหรอครับ
ครับผม
อ๋อครับ สวัสดีครับสบายดีนะครับ
สบายดีครับ อาจารย์สบายดีเนาะ
ครับสบายดีครับ
Sawadika, Pak Len.
สวัสดีครับนี่เอ้ยยังgaripak lah tu
I'm trying to share my screen but it's just my entire screen so
Yeah. Exactly.
yeah so can you see my screen now?
Not yet.
Yeah. No, one moment. So you do you see my screen now?
Yeah, I think so.
Okay. So I see that someone, so it's like my colleague from China, he's chatting that he cannot hear the voice, but for everyone else it sounds okay, right?
Yeah, we can hear you clearly here.
Okay, so he left, maybe he want to rejoin. Okay, so one moment. I tried to share just one window, but it doesn't look. Maybe I just rejoin again. So I would like to see the browser. So can you give me like 3 minutes?
Sure.
Okay. Yeah. Okay. So I will join again soon. Yeah. One moment, please. Okay, I'm back. So I will try to share my screen once again. Yeah. So okay, do you see the slides now?
Yeah. I think it's clear.
Okay.
But there is a humming noise from your side, I think.
Oh, okay. Maybe I just try to plug in my headphone. One moment.
Sure.
Hello? Can you hear me?
Yes, we can hear you.
Okay. So I can hear you clearly, Asrami. So I don't know whether it's better on my side now.
Well, okay. I think it's acceptable, but there
Okay.
is some kind of humming background noise.
Yeah. Okay.
I don't know whether others hear this sound or not. Maybe some.
Yeah, I do hear the humming voice. It's kind of like a noise. Do you have a speaker nearby? I mean, like, is it a speaker?
Yeah, I have a speaker, so I just plug in my headphone and I just use my speaker.
Ah.
So I am not sure where it comes from. Or maybe I try switching the room. So it's another option.
I think perhaps the speaker. Normally, it's like interactions between the mic and the speaker.
Okay, a speaker. So it's
Yeah.
like a feedback.
Ah.
But I have my headphone, so actually it should not be the feedback.
Oh, okay.
Yeah, maybe I just go to another room for. So let me switch.
Alright.
Another room. Maybe it can get better. I know it quite well, so it happens during the online presentation from time to time. Yeah.
Oh, alright.
So let me see. Or maybe I have to turn off my air condition, but it would be too hot. So yeah. One moment. Hello, Tess. So does it sound any better?
Yeah, we can hear you better now. There's no humming voice and no humming noise.
Great. So I just.
But there's it's acceptable. Yeah, it's okay. It's still we still can hear it. Sometimes no.
Okay.
But now it's okay. It's very clear.
Mhm. So yeah, I'm ready. So ready when you.
Ah,
So if on your side it's ready, just tell me. I can just
all
start.
right. Can we start now, Dr. Azrami?
Okay, okay, Ken, please, please.
Okay, but before that, Dr. Suramate, we will after the introductions, usually we'll take a photo before you start. Is it okay?
Yeah, it's fine.
All right. Okay. Okay. So I will start now. Okay. Assalamualaikum and very good afternoon. Especially to our Dean of Faculty of Electronic Engineering Technology, or known as Ftken, Associate Professor Dr. Azrami Abdul Hadi, Dr. Sophie Jack, our ACE, our head of ACE, and all the lecturers that attend this webinar. Welcome to our first African Research Knowledge Sharing webinar. So today we have a wonderful speaker from Thailand. His name is Associate Professor Dr. Suramate Chalermwisutkul. Is it? I'm pronouncing your name correctly? I'm trying my best. All right. So this is a little bit announcement for the audience. Okay. Please fill in the attendance form, which is a Google form. You may find it at the chat box. Maybe after this, Dr. Noramina will paste the link. Okay. So this link is important because you will get the e-cert after the webinar. And there will be also an evaluation forms that will be given at the end of our sessions. I hope you guys can fill in the evaluation forms so that we can improve this webinar on the next sessions. Okay. So before I start, before I start this webinar, I would like to share with you guys a little bit information about our speaker today. Associate Professor Dr. Suramate Chalermwisutkul received his Diploma in Engineering and Doctor Engineering degrees in Electrical Engineering from RWTH Aachen University, Germany in 2001 and 2007 respectively. In 2007, he joined the Sirinton University Thai-German Graduate School of Engineering, known as TGGS, as a lecturer and a researcher. He has established the RF and microwave laboratory at TGGS, where he has been holding the position of lab head from start. Dr. Chalermwisutkul has communication subsystem manager at Dr. Chalermwisutkul was communication subsystem manager of the NextSat project, in which the first time-made satellite was developed and launched to orbit by SpaceX Falcon 9 rocket SSOA mission in 2018. He was also a visiting lecturer at RWTH Aachen University, Germany, where he taught a seminar course in electromagnetic sensors for multidisciplinary applications. His research interests include RF system for CubeSat, smart antennas, reconfigurable RF system, and EM sensor. But before we start, I would like to seek cooperation with all the participants today to turn on your camera just for a little bit so that we can take a virtual photos for a group photo session.
Okay.
Is
So
it okay?
I hope. Yeah. Okay. I hope I come back on time. I just went to get my power cord.
Oh,
So,
okay.
okay, but it's okay now. So I hope you. So can everyone see my slides clearly?
Yeah, I can see. Did you want to go take your power
I
laptop
got
now?
it.
Oh, you
I
got
got
it.
it.
Okay.
Yeah.
Okay.
Okay. So all right.
Uh-huh.
So, yeah. Thank you very much for the introduction, and
All
I
right.
very honored for the invitation to give a talk here today. So actually, I should be teaching at RWTH Aachen University, the longer version of the course, electromagnetic sensors at RWTH Aachen University right now. But due to the COVID-19 situation, so I have to cancel the class. So I'm very pleased that I get the honor to present some activities about this topic to the colleagues in Malaysia and also international colleagues from other countries.
Dr. Suramate, sorry.
Yep.
Can you make it full screen, your slide?
Full screen. Yeah. Okay, it's fine. So I will just lose the screen of the.
Okay.
Okay, but
Yeah, this is
yeah. Okay. So it's just that I cannot see you, but unless it's okay. Okay. So the screen will switch totally to PowerPoint. So I don't know how to split the screen. But if it is fine for you, it's okay. I can start. Yeah. Okay. Then please let me move into the content of today's talk. Okay. So, all right. So as I suggested the topic, so it will be more on the applications. Yeah, and with a little more focus on the Southeast Asian countries. And okay, but if you are interested in more technical details and the design of the sensors and so on, so we can discuss afterward. Okay, so first of all, I would like to present the outline of this presentation. So it's a long story how I came to microwave sensing topic, but I will let you know how it came from. And yeah, when we talk about sensor, so there are no such a thing like a universal sensor that you can just take one and you can measure everything. So I will also mention what for what applications or what situation microwave sensors can be applied and what they cannot do. Yeah. So the major reason why we can use the electromagnetic fields or waves to sense materials or objects is that they have so interaction with the material or object in the reality. I will touch this topic a little bit, and then I will switch to different kind of applications with some focus on the biomedical application and in some of the chemical and petrochemistry. Okay, before I conclude the talk, I will mention a little bit how RF microwave sensors can be imagined as part of the IoT and smart city applications, which is an upcoming applications which will change our society. Okay, and at the end, I will conclude my talk. All right, so it was a long journey for me that before I came to microwave sensors. So I started to study, so as the colleague has introduced me, but to look into more details, I have done some work in VLSI design too, which means that it was related to so digital circuits on the chip level. Okay, so and for the PhD, I moved a little bit away from the VLSI design in order to learn a bit more on the analog side. And my doctoral thesis was about RF power amplifier design. So at that time, it was still for 3G application. So then I came back to Thailand, and it turned out that I have to teach antenna a subject that I have never learned before in the university, but it has some similarity with RF microwave circuits. And now, yeah, I finally come to microwave sensor research. Okay, so I have, as you can see, I have broad, but maybe not in-depth expertise in the topics that I have handled or studied. But for interdisciplinary subjects, it could be also for beneficial. Okay, so that was a big question after I came back to Thailand, because nobody produced power amplifier for 3G in Thailand. That was a little bit of concern. So I tried to like look around and find applications that would need my expertise in RF microwave. And to do that, one should ask himself before what what is the society, and what is the situation in your country. And when I ask myself, so, and it is, I think it is very similar for many Southeast Asian nations. So we have quite a great biodiversity. So, and some in the past, so our major industry was agricultural industry. We have a lot of biomaterials. So I know many colleagues in material science who has progressed their career quite well. So, and their research is of interest for people around the world. So we have a lot of solar energy too in Southeast Asia due to our locations. So, and our strong points are like food, chemical, tourism, logistics, and for Thailand, it's especially the medical sector too. So if you follow the news, you will see that we have managed the COVID-19 situation quite well. So we have always like less than 10 new infection cases, which are all imported cases. We don't have domestic new infection cases for, I think, longer than 60 days, something like that. Yeah, but there are also some challenges. So if I consider the economy in Thailand, so we focus pretty much on the previous strengths that we have. We are like manufacturing sites for many industry. We have like agricultural products, but sometimes we also have natural disaster like flooding and droughts sometimes. And we are also moving in the direction that the society will be changed by the digital technology. So people are familiar with online shopping and a lot of applications and IoT devices, which is aimed to make our life more convenient. And even though we have good medical sector, but still for the poor people, especially in rural areas, they barely have access to the medical services like people in Bangkok or in metropolitans. So those are the challenges that we have especially in Thailand. So if I would like to compare the situation with Malaysia, maybe I don't know the in-depth situation on your side, but you cannot compare Thailand with industrial park like in Penang, where you have a lot of technology companies and deep techs and so on. And so that when you study something, you know exactly when you go out for work who will be your employer. For Thailand, it's quite different. So for technology company, the biggest sectors maybe is the automotive one, and the other one that we have is like hard disk drive. Unless it's like something here and there, but not really in a significant portion. Okay, so therefore, I think, how can I apply my knowledge for these challenges? Okay, so when I consider applications of RF and microwave, so when we start to look around and try to connect ourselves to experts in different areas, you see that there are a lot of demands in microwave technology in other industry too. Yeah, on the right hand side, so you will see the bluish blocks, or yeah, on the left hand side, so you can see the colorful boxes. So there are like the applications that need expertise in RF and microwave. So, but it is not sufficient to just know about RF and microwave. You will need colleagues from embedded systems, semiconductors, mechanical engineering, even though we are in electrical engineering, so, and telecom. So AI will also play a big role in those applications, especially for the data analytics and how to interpret the measured data. So for the application side, we are directly linked to biomedical engineering. So you might have seen some publications related to sugar content in blood using non-invasive sensors. So also colleagues in the chemical engineering, they also have interest in using microwave, for example, in reaction acceleration, and also for the monitoring of reactions. So for material sciences, it's very natural because the interaction of electromagnetic waves at different frequencies with the material properties. So yeah, for food, for biology too, and as well as for environmental science. For example, if you would like to measure contamination in wastewater. So you see that we need a lot of expertise, and we also need a lot of experts to work together in order to provide the solutions that can help mitigating the pain points. All right, how I actually came to microwave sensing is actually by chance that one colleague of mine, she has like a need of sensors in order to sense the water droplet, which is made as an emulsion. So it's water in oil emulsion, and the oil that they use is the fuel oil, which is totally black in color. So so what kind of sensor would you like to use in order to measure how good the mixture is mixed, how good or how stable the emulsion is? Yeah. So I didn't know about this before, but my colleague told me that the smaller the water droplet is, the more stable is the emulsion. So it means that you can let it like still for a few days, and it still doesn't separate into two layers of liquid. It is still in the form of emulsion, but the difficulty is how to measure the droplet size and the amount of water that you have mixed into the oil. So optical sensors is like camera is almost not possible. If you consider to use the NIR, so the near infrared sensors, you can sense just at the surface of the sample, but you cannot look inside. So for X-ray, it is too bulky, and you will have a risk of radiation hazards. And I'm not sure whether it's appropriate for this application at all. Okay. And for nuclear magnetic resonance equipment, it is simply too expensive. But for RF microwave sensors, it can be so the measurement can be very fast, and I put it as a cheap solution, but it can be cheap sometimes, but sometimes it can also be expensive depending on the situation or the topics that we would like to use the sensor. So I put the word can be non-destructive because in some cases, microwave sensors are also destructive. So you have to put the probe, for example, inside the tissues in human or animal bodies. So, and one major advantage of microwave sensor is that if you choose the right frequency, so you can also sense into a bulk material, so which is possible, and it is not possible for many other types of sensors. So another studies that my colleague have done is like they would like to measure the amount of the surfactant. So for somebody who doesn't have chemical industry knowledge background, so like me too at the beginning, yeah. So the surfactant is some substance that you mix into the emulsion to make water being mixable into oil, for example, yeah. So a good example would be detergent, for example. So, but yeah, to save the surfactant, if you put it too much into the emulsion, it doesn't help anymore. Yeah? It will saturate the whole thing. So we have done some studies about that, and we got also some interesting results. And we can also determine the amount of the appropriate surfactant that you should add into the emulsion. So that was the start, how I came to microwave sensing applications. And I just took something I have got, so some sensors that my student had made in the past, and just go on and measure without any knowledge in material science. So, okay. So if we compare the sensors which use some kinds of wave in order to measure the material properties. So we have on the left-hand side in the black box, so the ultrasonic mechanical vibration. So here the advantage is that you can look even through metallic structures or shielding, which is not possible for electromagnetic waves. So, and a lot of researchers are also look into the terahertz regime in order to find some new solutions in sensing technology. For example, there is a word that I capture from some of biological colleagues. They are talking about exosome, which are some substances that you can subtract from the cell in order to find whether it's a normal cell or it is a cancerous cell. So this should be the substance that you can find using the terahertz signal. I'm not into it yet, but we have colleagues who are also working in that area. Okay, so for the optical sensors, so we probably all know about the camera, and some of the low-cost camera can do some work. For some more sophisticated work, you will need industrial camera. And as I told you, in some situation, it's not possible anymore if your sample is not transparent. So you cannot see the details which is embedded in the medium of your sample. Okay, so NIR could be something in between between the terahertz and the optical sensor. So you can sense only at the surface too, except from one thing, from one equipment, which is the synchrotron light. Just because of the high intensity of the synchrotron light, we have the biggest synchrotron center in Thailand, which is the biggest in Southeast Asia. A lot of colleagues in biology and in medical science are using this equipment a lot, but you can imagine how bulky it is, yeah, and how expensive it is. You cannot just go to the synchrotron light research center to measure some small food samples every time. Okay, so and as I did the work with this droplet size measurement, so when you look at the electromagnetic spectrum, and by considering the frequencies and the relationship of those frequencies to the wavelength. So when we would like to measure the droplet size of water in oil, which is normally in micron regime, or some of the cells like blood cells and so on, so it's also in this regime. So if you look at the corresponding frequencies to these dimensions, so we probably think, okay, now we are in the infrared and the visible light regime, yeah, but it turned out to be not so, yeah. So it depends on what kind of physical phenomena you are considering, yeah. This is a good lesson learned from that from the emulsion project that we have studied too, yeah, because I will mention to you in the next slide. So for microwave people, we have to learn we have to learn material science a little bit in terms of the relative permittivity, or the dielectric constant, and also the loss factor, which is the material parameter. So this is why we can use the microwave sensor. And the other thing that we can use in order to add the information into the measurement data is the sweep of the frequency, and therefore it is called a spectroscopy, so microwave spectroscopy. Okay, and when we sweep the frequency, so and you observe the dielectric constant of any samples, yeah, so we will see the typical graph of the dielectric constant, which starts at quite a high level and then it drops down at some specific frequencies. So this stepping down is due to the different physical phenomena. So if we look into the RF microwave regime, so we are considering these two physical phenomena, which is the so-called interfacial and space charge polarization, and also the orientational dipolar polarization. So for the colleagues in terahertz and yeah, the higher frequency, yeah, optical, so you are considering this regime. Okay, so right, so and this is the how it looks like if we present it in form of the size of the effect. So the water droplet that we had embedded in the oil as an emulsion, it is still considered quite bulky, because it is not the size of the cell or the size of the droplet which matters here. Actually, it is the charge distribution that you have on the surface of each droplet, like this, yeah. And if you consider this, it is like you have polarization of each droplet, and if you have a lot of them, you have a lot of polarization phenomena happens in all the droplets that you have in the system. And this happens, to my surprise, at that time in the megahertz regime, yeah. If you consider some slides back, so a few slides back, even though the size of the droplet is in micron, but to sense the size of the droplet, you don't use the corresponding frequency range in terahertz or in optical regime, but actually in the megahertz regime. So I have a colleague who is a renowned professor at Chulalongkorn University. This is the university #1 in Thailand, and he has studied this effect very, very intensively. So he can manipulate human cells. He can like tear out the cell membrane and put something inside and close it again. So it is very, very amazing. Yeah. Okay. So what I did in the past is more the dipolar orientation, because I also had some activities in microwave heating, and actually we are focusing more on the phenomena in this frequency regime, which is similar to the frequency that we use for telecommunication, like Wi-Fi 2.45 gigahertz. It's the same frequency that we use for microwave heating too. So for the vibration in the atomic level, like in the crystal, so the frequency is very high. So we are not looking into this within this talk. So there are other colleagues who are dealing with this high frequency effects. So the frequency increase with this physical phenomena, and the phenomena will become more and more smaller. Okay, so yeah, this is the interfacial polarization that I just mentioned. So you can consider different scenarios. For example, if you have conducting sheets embedded within liquid, something like that. So this is called the Maxwell's model. Or if you have the droplet, it is called Wagner's model. Or if you have some spheroidal objects within the medium, so it is called Szilard's model. And one is always a little bit clever after the first experiment. Yeah, our experiment have used the 2.45 gigahertz frequency in order to measure the droplet size. And it turned out after the student has come to the end of their bachelor project that, oh, actually we should have been using the lower frequency in the megahertz regime. Yeah, if you ask me, so the 2.45 gigahertz can be used also to determine the number of the amount of water within oil. This went well. With the surfactant, the amount of surfactant, it went quite well too. We saw some trend, but it would be greater if we use the megahertz regime. So we just left the study there. It's a little of the pity that students graduated and my colleague did not pursue this research anymore. So if you are still interested, it can be picked up. And this time we would use the megahertz regime in order to measure this effect. All right. Okay, so it's similar to the people who are making supercap. Yeah, so you try to embed some other materials. So it's like a colloid or mixture. Yeah, that we have learned in high school. Yeah, so my son is learning this too. Like this is, for example, for colloid. So yeah, okay. So we see also people who measure the droplet of water in the microfluidic channel. So you build a small channel and let the water droplet flow over the interdigitated capacitor, and you can measure the speed of the drop which is passing through this micro. So by measuring the time, so you can measure how fast the droplet moves. And by measuring the the capacitance value, you can also detect how big is the droplet. Okay, so the same group of people has done another investigation, and now they can measure the speed, they can measure the size, and they can also measure the content. It's like if you have a droplet of water and a droplet of, let's say, alcohol, it will act differently. Okay, so and this is all done in the megahertz regime, right? So and so with that study, I have been working with another group of colleagues who are focusing on the microfluidic research. In the team, we have the Thai Microelectronic Center, the other centers of the National Science and Technology Development Agency. We have Chulalongkorn University. So, and the colleagues from Chulalongkorn University, we have mechanical engineers, we have veterinary medicine, yeah, so the doctors for animals, and they would like to measure like cancerous cells of pets and so on, yeah. Okay, and this work is related to a single biological cell, so you have to separate it and isolate it effectively using the microfluidics channel, and then we can start to apply the electromagnetic fields or wave to that single cell. And this work of artist has described very well the effects at different frequency. So for the DC to megahertz frequency regime, so actually we are measuring the cell membrane, yeah. So whatever happened to the cell membrane can be detected at this frequency range. If you would like to detect something within the cell or the content of the cell, so from the physics, so the microwave regime should be the right frequency to use, yeah. And if you would like to measure it at the atomic level and very, very small amount of differences, so we probably want to use the terahertz regime. Okay. All right. So there are some work in single cell detection using microwave regime too, but there is not a lot of work that we have seen so far. This is still subject to research, and it is very challenging because the differences within the cell is quite small, that it is barely detectable. So we would need the very, very sensitive sensor in order to differentiate between different kind of cells or normal or abnormal cells. But in principle, it is possible. So it is just the matter of how we can increase the sensitivity. Okay, this is this work. So this is still the work related to single cell analysis. Similar to the bulky application, when you consider microwave sensor, you can also consider heating it up. So in this work, they have applied the microwave energy like a microreactor in order to heat up the droplet that is transported through the microfluidic channel. And they have some reasons to inject the thermal energy into cells or into droplets. It is like a micro reactor that you can generate some kind of substances or medicine, and also to manipulate cells. Okay, so now we move a little bit more from one single cell to groups of cells, or sometimes they call it cell spheroid. It is now easier for the microwave sensing in order to see the difference. If it is not a single cell, but you have group of cells or tissues. So this is quite a new work that I have seen. So they use the millimeter wave in order to detect the skin cancer. So by moving the probe over the skin, and if there is some area which is prone to skin cancer, so this kind of sensor can be applied, and they have shown successfully that you can differentiate between normal cell and cancerous cell area. Okay, so actually we have made also similar. So they call it surface integrated waveguide, but in our application we made a sensor for the hard disk drive industry. So they want to generate magnetic field at the end of the probe in order to find some abnormal magnetic layers of their material. So it can be done. Okay, so this is any colleagues who have followed me for quite some time. This is the slide that I have to show every time. So because in the first semester, my student asked me, why do I have to learn Maxwell theory? Yeah, because it's so difficult and not so friendly for students and so on. So this is like my answer after 10 years of teaching. So I let the student buy the Coca-Cola, yeah, so drinks. So it's, we call it like black water. So we bought like 4 brands of black water, and then we measure it using a cavity resonator, and indeed you have you can see the differences of the frequency responses, and it is just simply, so you know what you give to your kids to drink. Yeah, it's just water and sugar, yeah, in general. So we can measure what kind of drink is more sweet. Yeah, if it is more sweet, it is less polar, and the resonance frequency will shift to the lower frequency. Yeah, so, and from that, or for this from this sensor, we have got surprisingly a lot of projects from the industry, from the petrochemical industry, for the food industry, and so on. Yeah, we use this cavity in order to measure the oil droplet too. But as I said, it worked a bit, but it would be better if we would use lower frequency for the droplet problem. All right, and my student went to Germany, and he did some studies in terms of measuring the wastewater in terms of heavy metal contaminants. And for RF microwave engineers, this is just nothing. So you just take the SMA connector, calibrate it at this end, and fill it up with the solutions, and that's it. Yeah, but for colleagues in other areas, it's quite amazing to see that if you have different kind of heavy metal contamination, so you see that the peaks, yeah, the peaks of impedance happens at different frequencies. But if you have the same metal but different concentrations, you see that the peak happens at the same frequency, but the magnitude is different. Yeah, which is very, very reasonable, because they have different conductivity. Yeah, again, here for zinc, the latter was for copper. So same frequency, but different magnitudes. Okay, so, and this is another sensor that we have developed in our lab, and it was presented in EUCAP in, I think, 2019. And the problem was, like, we can use the coax cable in order to measure liquid. But the problem is, if we put the probe too near to the bottom of our container, so you don't measure the liquid, you measure the bottom of the container. or if you are very near to the surface of your liquid, so it's the surface of the liquid will affect your measurement result too. So we have developed this coax sensor that you have two plates at the top and the bottom, and we have proved also that the surface of the liquid and the bottom of the container does not disturb the measurement result, and we can use it in order to measure the ethanol in water concentration. We have done some demo, not with this sensor, but with the cavity sensor, in order to differentiate between 70% ethanol and 68-69% of ethanol too. So, and you know why is it important? Because at the beginning of the pandemic situation, so everybody is buying this ethanol solution, and some of the manufacturer, they just decrease the amount of ethanol in order to save costs. And with microwave sensors, you will be able to check it real time. So, okay, so you'll find, yeah, we talked about the single cell characterization. So that was more on the megahertz regime, yeah. So it's like a mixture or the colloid. But if we talk about chemical solutions, so we normally use the microwave regime to measure the different kind of solutions and also chemical substances. So therefore, it can be used for characterization of different materials, like for food, for pharmaceutical industry, for cosmetic industry. They use a lot of this colloid or solution. You can use it for polymer science or plastic and other products. And for the purity of fuel, so this is also an interesting area that you can work together with the petrochemical industry and medical applications for sure. So we have seen in the research some of the probe that you can use to measure how the hip fracture is healed. So you know the problem with the aging society. So if the elderly people fall down, so their hip is broken, and it is a very painful thing, yeah. And in order to monitor how the muscles and the tissues is fixing itself again, this can be sensed by microwave sensor. I have seen some publications about this too. So, but the major point of microwave sensor is that people will come and will tell you, why do we buy a very expensive VNA in order to measure potatoes, something like that. Yeah? It sounds not very reasonable. So you have to make your own VNA sometimes, at least to measure reflection or transmission at some frequency. We have done that, and we found out nowadays you don't have to build it at all. You actually can buy it from China at a very, very cheap price. Yeah. So, okay. So there are some other groups who have done quite impressive work. Like this group, they have developed a palm top sensor for biomedical applications, and it can work from 9 megahertz up to 2.4 gigahertz. So the cheap VNA that I just mentioned to you, it can work up to 3 gigahertz already nowadays, but you get what you pay for. Yeah, so don't expect low noise or high dynamic range. So, but you can use it for some applications. So this group has proposed also very, very impressive work, and they created like an on-chip system with the RF front end with the sensor embedded, so integrated together, and then you can measure up to 50 gigahertz, which is very, very impressive. So why is it interesting? It is because you can have a small equipment that you can provide to medical doctors in rural areas in order to check the health of people and let them access to the medical services. So now we should talk a little bit about the integration with IoT. Yeah, so we all know that the world will be changed totally with the upcoming IoT movement. So you put sensors everywhere, and they communicate also with your backbone, communication backbone. So we just focus on this thing. This is the features of IoT devices as mentioned by this white paper. But if you compare the IoT devices like sensing organs of human body, so you get the information, and the information will be collected, and at the end you will save everything at the cloud, and here it comes that you will need experts in machine learning and AI in order to do data analytics for medical applications or for the chemical detection, as I already mentioned. So, and this is a real project that we get from the petrochemical industry. So what they have is that their substance can be not okay for some time, yeah, and they have to react by putting some other chemicals into the tank in order to mitigate the situation. And how they check this is nowadays is that they will go to the plant, take the sample, and run to the lab and wait at least half an hour to see whether there's something wrong or not. Yeah. But actually, it's more clever if you can put the smart sensor there. We use microwave sensor for this project, and here we will need IoT experts in order to gather and send the information to the gateway and then to the cloud. Yeah, the response can be much faster. Okay, so we are also collaborating with LoRaWAN company. So the managing director is my PhD student, and he gave the project to one fellow master degree student to design miniaturized LoRaWAN antenna at 900 megahertz. You will be amazed when you measure the antenna that you get from the market and they use it for LoRaWAN and IoT devices. The matching is terrible. Yeah, almost all of them. Okay, so yeah, we have seen the event that Elon Musk has presented the interface to the brain, yeah, using the electronic devices, and this is also the trend. So this is some work from this group, and it is a capsule that you can swallow, and there are some antennas which communicate wirelessly from in-body to on-body devices. So it's like LoRaWAN or IoT in your body. Yeah. So this is also very much of interest. Okay, so but besides, we are doing also other activities in our lab. Whether you call it sensors or not can be discussed, like RFID for many applications. So we have also some research in energy harvesting. So it is related to the RFID or the sensors too. Yeah. So we have antenna design and test measurement in anechoic chamber. And still we are following the space applications and the antenna for satellites. So we are still working with some partners in Europe. Okay, so, and you know, nowadays when you watch YouTube, yeah, so at the end of every exciting, interesting talk, you will see advertisement. So, and as the same as here. So I would like to share with you that every year we have the DAD scholarship. We are supported by the German government for Southeast Asian students. This is very special. Thais cannot apply. Right? only like Malaysian, Indonesian students, they are prioritized. Yeah, if there are still some slots, we also have people from Africa. Like this is my students. The three are my students. They have all done their thesis in Aachen University in Germany, and this one he has found the PhD position with my colleague in Ireland. Yeah. Okay. So it's a good opportunity, and I'm also open to work with colleagues around the world. Yeah, using this kind of support from the German government. Okay, and currently I am also recruiting a postdoctoral researcher for the grant that I have applied to the university. So the eligibility is a little bit strict. So with two Web of Science journal as first author, I know this is not easy, but okay, yeah, there are also some applications that I have got. Just the timing is not right. So if you know someone who would be interested, so we can discuss about this too. So, okay, please let me conclude my talk. Sorry, maybe I just took a lot of time. So, okay, so RF and microwave sensors, they can do something what other sensor cannot do, but also vice versa. Yeah? They are not something like a universal sensor. So the advantage is also that it is an electrical signal, so you can digitize it directly, not like so for camera sensor. So you can digitize it, but it's not always successful with the image processing and so on. And sometimes it's too bulky. And the other advantage is the measurement into bulk samples. So like big samples. So you can choose the right frequency, and then you can look through big material too. Okay, it can be made small, yeah, as I have shown you. And you can use it for monitoring in medical applications or in power plants or in chemical industry, environmental monitoring, and so on. It is, and it will be one important part of the smart city and industry 4.0, especially the food industry, the chemical industry, and it can be combined with any IoT standards that we would like to. Okay, but last but not least, you need many experts from different areas to work together so that they can share with you their pain point, and then for me as a IF microwave engineer, I can tell them what would be possible and what would be not possible with microwave sensors, so that at the end we have the right solution. It's not for the sake of we want to do this kind of research, but the expectation must be discussed at the beginning. Okay, so yeah, I have come to the end of my presentation. So yeah, thank you again for your interest, and if you have some questions, if the time allows you, so please feel free. Okay, thank you.
Thank you, Dr. Suramate, for the presentation. So I would like to open the floor for the questions. Any question from our member here? Let me check the chat box.
Dr. Sai, I think there is one question in the chat box.
Oh, okay. I was wondering. Thank you very much. All right, there is one question from Associate Professor Dr. Cheng. Prof, in your opinion, in your point of view, why is it required to conduct lump element circuit analysis on any inhomogeneous biological material, especially?
So I think that it is it is just the physical phenomena, and they would like to make some models in order to be able to at least simulate what can be expected. I just see, I didn't see into the details, but I would guess that the colleagues in that area, they would like to make some mathematical models or electrical models to be used during the design of the sensor. I think that would be the point, that they have studied the lumped element circuit analysis. Yeah. Yeah. Is it the right answer that you expect, or is there any additional comments? I mean, I have also heard from other colleagues that you can really measure difference of biological cells if their cell membrane is different. For example, for malaria. So this is shared by another colleague. If somebody get infected with the malaria, so the red blood cell, the cell membrane will be modified so that you have different structures. Therefore, the capacitance value of the cell membrane is increased. That is why I think they would like to study this lumped element circuit analysis of biological material.
All right. So I hope it's answered Dr. Cheng questions. Dr. Cheng, is it answering your question? Is Dr. Cheng still here? Dr. Cheng, are you here? Did it answer your question? Oh yeah, I'm here. Are you
It's not working well. Oh, it's
all
writing.
Ah, I see.
Writing another question. Okay.
Okay, so maybe in the meantime, maybe just a very a more practical kind of question for you, Suramate, that maybe we could discuss. It's about the practicality. So let's say, I think in our countries, we don't really have very high-end equipments, and some of the measurements, especially involving cells, will need to be measured using those. Maybe at 60 or maybe 100 gigahertz, right? So what, maybe in your opinion, what do you think of how we could, get this sent out to our collaborators, or practical issues on how to overcome this problem?
Yeah. Okay. So thank you for the question. So it is indeed the discussion when we talked about this kind of research. But as you have seen from the slides, so in terms of compactness, it would not be a problem to make compact VNA at 60 gigahertz anymore. So it is not a problem. In terms of price, it is always a discussion. So which means that if you get the economy of scale, and if you can also like expand the market, normally we use VNA for the telecommunication market and so on, but you can also expand it to the medical area. So if it is scientifically proved that in this frequency regime you can measure or diagnose something, so you can think about producing more equipment, and so that the price can get down. So the size doesn't matter anymore. I think it's not a problem. So you can have a very, very compact devices to measure like blood samples of patients and so on. This is not an issue. So but the issue of price is true. So in terms of terahertz, there are a lot of research, but here you are right. I think this is not very soon to be expected that the price of terahertz measurement equipment or even higher gigahertz regime will be very low very soon. Yeah, so it is quite a lot of scientific work ongoing in the terahertz regime, and they more and more they publish some interesting findings. But yeah, as I said, so it must be convincing enough so that the measurement equipment can be made cheap and accessible for everyone. So that be my observation.
Yeah. So maybe Suramate, in the meantime, that the only way that that we could get our samples measured at the terahertz frequency, for example, is probably by collaborating with overseas university.
Yeah.
And maybe, I don't know, maybe you could have some comment on what are the maybe precautions, or because these are where we're dealing with cells, right? That we need to send out to overseas countries and things like that. So yeah.
So frankly speaking, I do not have a lot of experience in this. Yeah, I know the problem well. That so you need, so you just mentioned that you need to send samples to overseas.
Yeah, for example, or maybe how can we preserve the integrity of the samples and so that it's it's, in a situation that is as what we intend to measure.
Yeah, it's a very good question. So I don't have a direct answer for you, unfortunately, Jack. So I think so the colleagues in the medicine can answer this better. So because they have experience in this, and I think it's quite a common practice that you send samples abroad for measurement. Yeah, as I said, I really don't know how to, but it happens, and it seems to be like common. Or you just fly to Thailand.
What about your colleagues in Chulalongkorn? Maybe they have already some good equipment that's able to be,
Chulalongkorn might have some facility, but from what I know, so the NECTEC, the National Electrical and Computer Technology Center, yeah, they have this facility, the terahertz facility. But when we talk about terahertz facility, it could be very, very different. So the terahertz facility that NECTEC has is like quasi-optical. So it's more handled like optical equipment. So it is not like the University of Leeds. There they have, they also have something which is like lower terahertz range that you need VNA or something like that. But the terahertz for other colleagues, it's really high. So it's nearly optical, and they handle almost everything in the as a optical equipment. But you will see some similarities, like you see split ring resonators and so on. So it's very similar, but the way they excited this is quite different from what we RF microwave people have experienced. Yeah. So when we talk about terahertz, we have to ask which range really. Yeah.
All right, thanks for it.
Yeah, okay, thanks.
Thank you, Associate Professor Dr. Jack, for the question. Any more question? Oh, hang on. Dr. Chang just wrote another question. Wow. All right. The question is, when I submit an article to journal which involve lump element circuit analysis, I always been asked what is the importance to study and biological material from the perspective of an electrical and electronic engineer. It is hard for me to justify it as I just conduct this analysis because I am curious about the electrical behavior, of an biological material. I studied it from angle of dielectric. I have no meant to solve any engineering problem. Can Prof advise me when I met this question again?
Mm. Yeah, yeah,
Okay.
sure. I mean, we can discuss in more details if you want. Uh, so I think we need to come to the root of the problem when we talked about this. When we talked about sensors, we want to detect something, and it is always important to have the sensitivity. Yeah. So and this sensitivity is translated by the electrical signal, right? So therefore, you have to study the electrical behavior of the samples, because at the end of the day, you would like to translate something which happens electrically to the phenomena or to the happenings within the cell. Yeah, as I said, if the cell is get infected with malaria, so the cell membrane got modified, and it means it is a change in the capacitor. So at the end, you cannot, because you don't look at it. So many medical people are very convincing. I had a lot of discussions with medical people too, and they are very convinced of what they see. They see, if they don't see it, they don't believe it. So therefore, the medical people always love to see something being sensed using optical sensor, because they see it in real and they believe it. Yeah, but for us electrical people, so the change in electrical signal can be interpreted as something which is happening to the cell. This is you need a lot of convincing arguments that is true. Yeah. So at the end, we will need assimilation of different sensors. So, but we also have to point out that, okay, if we want the high-speed camera and you can have the cell running through the microfluidic channel, and you can see whether that cell is normal or abnormal. I think we have to prove to them that if electrical signal is changed, so it can be interpreted that the cell is also changed. Sometimes even if they don't believe it at the beginning, but what we can also propose is like a very fast detection. So if you use electrical signal, it is very fast, so you get the result like in real time. It can be a pre-check, and then if you feel okay, it can be something wrong, you can still use the camera in order to zoom in and use the microscope to really look into the cell, what is happening there, and so on. So I have a use case for this, and the colleagues in another hospital in Thailand, they face a lot of problems at the borders of Thailand, because now we are importing workers from neighboring countries into Thailand, and there you need the health check of those people. And imagine that you have to handle like 10,000s of cases in a few days. Yeah, so you cannot just take blood samples and look like 10,000 times into the microscope to check whether they have worms or not. Yeah, so this is where the microfluidic research group has proposed that you can like inject the blood sample into the channel, and then you can detect whether they have worm eggs or something in their blood. Yeah, and if you use electrical signal, it could be much faster. You can like pre-screening some of the cases out, and then yeah, you like can take the pressure from the shoulders of our doctors. They have enough to do nowadays. Yeah, that is really a point that we have to discuss with our medical colleagues and convince that that they will get some benefits from the electrical model. I would say so.
Okay, so Dr. Chang replied, okay, I got it. A potential study for development of sensing system. Thank you, Prof. Your words are inspiring. So any more questions from members of the floor here? Let me see the chat. Right. If there is no more question, can we take a photo again? Because before we start the presentation, we're supposed to take a photo, but then we have some kind of technical issues there. So can we take a group photo in a while? Can everyone turn on the camera? Oh, Mr. Russell, do you have a question?
Yeah.
All right.
Yeah, I have a question. Thank you very much. First of all, thanks Suramate for your nice presentation. It was really great. I'm from actually Dalian University of Technology from China, and I'm very curious about that. Can you tell us that in respect of high frequency, the high frequency range, what is the future for environmental application of microwave sensor? Which area we should focus on in terms of to deal the current environmental challenges?
Yeah. So I get in touch with
as I'm one of the environmental.
Yeah, I see. Okay.
Expert, and also we are facing a lot of.
Yeah, so the time that I get in touch with environmental people was this wastewater measurement, and I think that is one potential application, definitely, because I got also contact from the people from UK. So for us microwave engineers, we thought, oh, it's very simple measurement, and we also get scared that our publication will get rejected because of the simple setup and so on. But it turned out that people get interest in that, and it seems like it is a realistic application for the quality of water, for checking the quality of water. And as I already mentioned, I think that the advantage is in a real-time measurement and monitoring. And from what I also have seen in other applications is for the landslide. There are also people who are working in detection of landslides. This is not exactly the material measurement, but maybe they detect the change in structures or in mechanical modification of the structure, so that you can detect the landslide quite easily. So there are some colleagues of mine doing that using RFID, embedded RFID in the area where you have a lot of landslide. And I also know that the landslide can also be detected using the radar technology. So to be very broad, radar technology is also one of microwave sensor technology too. So that can also be related to the environmental science. And so that radar is also used pretty much in order to do the coastal monitoring, whether you have like big waves coming or things like that. Yeah, so I see that radar has a lot of potential in environmental science, and you can also, yeah, in terms of remote sensing, if you like. But if you want to localize the measurement, you can also embed the microwave sensor into soil or into other other environmental things in order to measure right at that point. This is also possible. Like soil moisture or like contamination in soil. So we would need some help of the electrochemical people too, because sometimes the electrodes are not sensitive enough. So at the end of the day, you will need some coating. You will need to coat the electrode with some special substance or ceramics in order to send some specific gas or some specific substances, which is very common. I have seen this a lot of time. Okay.
All right, thank you. Any more questions?
I just have one more comment. So as I taught at RWTH Aachen University once, I assigned the students to propose some topics that they would like to use the microsensors. And there was one interesting application from a Chinese student, and they want to sense the jade, whether it's a real jade or it is a plastic. So I think it's a very nice and good application. Yeah.
All right. Any more questions? So if there is no more questions, should we end this webinar? No more question, right? Okay. Thank you very much, Dr. Suramate, for the very nice and information scope webinar today, for sharing your knowledge with us. But before we end this webinar, I would like again seek cooperation from everybody to take a group photo. Can you guys turn on your camera? Then Dr. Nuramina will capture the screen, and then we will share in our Facebook. Is it okay, Dr. Suramate? We take a photo for a while before we end this.
Sure.
All right.
Can somebody please count?
I think right. Usually Dr. Nuramina will count.
Okay. All right. So waiting for everyone to turn off their camera, right?
Where is it? How to? Okay, 1, 2, 3. Okay, hold on for a second. Okay, one more time, right? Okay, 1, 2, 3, smile. Okay, thank you very much.
Okay, thank you very much.
Thank you very much, everyone. Thank you, everybody.
Thank you, Suramate.
Thank you, Jack. See you then. Talk to you.
Thank
Bye-bye.
you, Dr. Suramate.
Bye-bye.
Bye.
Terima kasih semua. Assalamualaikum. Waalaikumsalam.